All right, Joel David Hamkins, thank you so much for coming on my show.
Well, it's a pleasure to be here. I'm happy to talk to you about anything here.
Oh, terrific. I wish more people I emailed had that attitude, and maybe I'd have more episodes. So let me say to you and to my audience why you're here. You are a set theorist and a logician at Oxford University. In fact, your appointment is it in the philosophy department?
That's right, although I'm also affiliated with the maths department, and I have maths PhD students and so on, as well as philosophy students.
Okay, I just wanted to check. I mean, I see you as a mathematician. So this is a great opportunity, I think, for me as a mathematician in a very different field to learn about the field of set theory and logic. Or if they're one field, two fields, what's going on? What's their relation to the rest of mathematics? There's a lot of interest in this subject. I've never had the opportunity, I guess, to talk like this. Maybe I should have when I was in academia. There's a lot more to it, though, than just one field of mathematics, because I'm sure you know, a lot of people ascribe a lot of philosophy to set theory and logic, and that it plays a role as a kind of foundation for mathematics. It's almost meta-mathematical. I don't know exactly what your views. I'm very eager to hear what you think about that. And of course, I also recently had a discussion with another mathematician, Norman Wildberger, here on this show, who has some sort of controversial views about set theory. He rejects some of the, I think, standard accepted axioms of set theory, but maybe some of those axioms really are controversial. And I debated him from my perspective, but you know what? I'm not an expert in that subject, so I'm coming to you for a second opinion. So let's see what we can learn here. I want to talk about a lot of math, but just quickly first, I just want to know a little bit about your background, so who you are. So where are you from? How did you get to be into your subject?
Right. So I'm American. I'm from the US.
Okay.
I did my undergrad at Caltech in Pasadena, California, in mathematics. My undergraduate degree is mathematics, and then I did my PhD at Berkeley. And then
your advisor was Hugh Wooden, right?
That's right. Yeah, exactly.
So I think he's the only. I once heard a presentation of his. I was visiting Berkeley as a grad student, and he talked a little bit about how we should decide whether or not to accept the continuum hypothesis. But
that's right. Yeah, he's big on that. He's very inspirational. He was a very inspirational supervisor. Of course, this was many years ago. But and then I went to New York. I was at the City University of New York for about 25 years, teaching on the faculty there in mathematics, philosophy, and computer science. But also I was visiting at many other places, Carnegie Mellon and in Europe at a few places. I was in Munster and Amsterdam, and also so I would often take leaves from CUNY to go to other places. But eventually, what happened? So I'm a set theorist in training. My dissertation was in set theory, and I've done a lot of work in set theory, but also logic generally and computability theory, and I've even done some work in group theory and some other things. But the work in set theory started touching more and more on philosophical issues, as it does. And this was also true for Wooden. I think his work started becoming increasingly philosophical in certain respects. And so basically I seem to have turned myself into a philosopher, and so I wear multiple hats. So that's why here in Oxford, I'm professor of logic in the philosophy faculty, which is my main appointment.
What do you value more highly?
Oh, I have to order them? Oh, God, that's impossible.
Okay,
Of course. I mean, I appreciate all the aspects. So one of the things that's so interesting to me about set theory, my interest is mainly in set theory is because it seems to shed so much light on the nature of infinity, which is, of course, an inherently philosophical topic. If you look back in history, sort of the puzzle of infinity and figuring it out and so on. It can't really just live in mathematics only. There's always going to be philosophical aspects. But also set theory has this other philosophical aspect as because of the role it plays as a foundation of mathematics. And so it's engaging explicitly with many extremely philosophical questions. And oftentimes, well, what I enjoy most about that aspect of the theory is when I mean, it's this sort of virtuous cycle. You have a philosophical question, then what gives rise to a kind of mathematical analysis, which then is mathematics, and you can prove theorems and so on, just like any mathematician would. But then it sheds light on the philosophical question again, which then raises further, maybe more refined philosophical questions in light of the mathematical results. And so it just is going around. So I love traveling around that cycle, and I've done it many, many times.
I see. That seems to be a useful way of a relationship between math and philosophy. I guess I come from a culture in math that's very suspicious of philosophy. If you start doing philosophy, you're doing the wrong thing. Maybe they think you can go off and never make progress or I don't know.
Well, it seems to me that a lot of mathematicians have sometimes strongly held views, these sort of anti-philosophical views, but the fact of the matter is that actually a lot of the time, those people don't really know any philosophy, or they don't know very much philosophy. And so they have this negative opinion, which is based in a kind of fantasy or a misunderstanding or ignorance of the subject. There's really a huge amount of extremely interesting work going on in philosophy by philosophers who are mathematically trained. I mean, this huge community of philosophers who are mathematically trained, like myself, but I'm not the only one. There are, many, many people in philosophy who have mathematical PhDs and so on, and really quite knowledgeable. And they're doing such interesting work that's often shedding light also on the mathematics, and is leading to mathematical research programs and so on, or interacting with them in a quite substantive way mathematically.
Within set theory and logic, or also within other areas?
Yeah, within other areas, not just set theory and logic, but also there's certainly other areas, like proof theory, for example, has this feature also. I mean, people doing proof theory are often, there's often extremely strong philosophical connections and issues that arise with proof theory and logic generally, computability also. I mean, if you look at, for example, Alan Turing's work, I mean, his famous 1936 paper in which he invented Turing machines, but also described what does it mean to be a computable real number and so on. This paper is just incredible. And is it math or is it philosophy? Well, I mean, it's just impossible to classify it that way, because that paper itself was introducing whole fields of mathematics that have grown and now have thousands of papers being published in them in computability theory, and it led to eventually to complexity theory and computable analysis and so on. Whole fields of mathematics grew out of that work, yet the paper itself is mainly read by philosophers these days, because of course mathematicians don't tend to read original works, but they read the later derived works that were written by later authors. So it's also a kind of cultural difference in the way that we relate to that paper.
Yeah, I can certainly believe that that's an important paper, and you bring up an interesting issue that maybe we'll be able to tease out, like where is the boundary between math and philosophy, or do you have any kind of sense of what that is? But instead of trying to prescribe an answer for that at the outset, sure. How about, here's how I like to start in the beginning. We'll start simple and go from there. Right. I've asked some of my guests, how do you explain what it is that you do to a layperson? And then we can build and then talk to a mathematical audience.
I see. So I guess the way that I would explain it to a layperson is quite different from how I explain it to a mathematician.
Yeah, I'm always curious because, right. It's a hard thing to do.
I work on a lot of different things, and all of these things, well, they're sort of unified by the mathematics and philosophy of infinity. This is what I'm really interested in, sort of aspects of infinity as it relates to mathematics, including philosophical aspects of infinity. And so of course, this is connected with set theory and large cardinals and also forcing and different universes of set theory. And that has philosophical aspects about the foundations of mathematics. And it's super interesting.
You
For
don't
example,
use you don't use those terms right off the bat with
yeah,
the
probably not. No, but so for example, I have a bunch of work on infinite games. So there's some work on infinite chess that I did. Imagine playing chess on an infinite chessboard with no edges and maybe even infinitely many pieces. And so we could imagine, well, what does it mean to play such a game, or what does it mean to have a strategy? And is it always the case that from every strategy, from every position, that one of the players would have a winning strategy? And how can we judge how close to a win a given player is, and so on? And so it's really quite a lot of interesting work about infinite chess. But also, I have a student now who's doing infinite checkers or drafts, as they say here in the UK. And he has some similar results there, also infinite hex. And we've looked at infinite Go and infinite Sudoku and so on.
Is that at all? I'm hearing some echo on your side. If
oh, I'm sorry. Is it? I don't know what to do about that. I don't hear any echo.
Okay. Sorry. So is that at all like I have a little bit of background in statistical mechanics, and you want to take the limit of something like the Ising model or percolation, and that fills up. It's a little bit like a game. I've also wondered about some questions about, like, say, Minesweeper in the limit.
Oh, I see. Oh, infinite Minesweeper. Oh, we haven't done that one. Yeah, I gotta put that on my list. So with infinite chess, for example, my interest in that started from a question on math overflow by Richard Stanley a number of years ago. It was about 10 years ago that he asked. And so the question was, can you have a position in infinite chess where, say, white has a winning strategy, but it's not made in n for any n? So in other words, is that situation possible? Or at least this is a question related to what he asked. So in other words, imagine a situation where one of the players can win, say white can win, has a winning strategy, definitely is going to win. What does it mean to win chess? It means to make checkmate, and that happens after finitely many moves. So
this is a thing, by the way, that I have never accomplished in my life. I have never won a game of chess, I think.
Oh, no.
I'm not big into the game, and even I know how the pieces move. And yet even like little kids, somehow I wasn't even allowing them to win. And I'm not good at games that I haven't tried to figure out yet. So I don't have a winning strategy, white or black. Okay, but continue.
So the question is, does it make sense to say even that is there a kind of built-in uniformity in the sense that if white can force a win, then is there a uniform bound on how long it would take?
Mm-hmm.
Right? So it's sort of like the difference between continuity and uniform continuity or something like that, right? Or and what I proved with my co-author is that no, you can have positions with infinite game value in the sense that these are positions that white can definitely win infinitely many moves, but black can control how long it takes. And that situation is quite interesting. So black can say, yeah, I know you're going to win. Okay, but this time it's going to take you 25 moves at least. Or maybe they start again from the same position. And black says, yeah, I know you're going to win, but this time it's going to take you 1,000 moves, or a million, a billion. He can say any number. And then they can play, and he can make it take that long. And that's sort of difficult to imagine, but these positions exist. And then you can say, well, could there be a position? So that's what it means to have game value omega, the smallest infinite ordinal value. But you can have game values that are higher than that. For example, could you have a position so that infinitely many moves you would reach such a position, but black could control how long it took before you got to that position? So that would be a position with game value what's called omega plus omega, because it's sort of like counting down from these ordinals. So counting down from omega, if you count down from omega, if we play the countdown game from omega, and then let's say you lose when we hit 0. Okay, and you're going to start first. And if it's a successor ordinal, you can only go down by 1. I can only go down by 1. But if it's a limit ordinal, then maybe
We're going to have to go backwards a little bit, I think.
Okay.
Because that's one of the things in my confusion. I feel like I know what cardinality is, but I've
Right.
never really understood these ordinals or what is going on there. I understand. I think they're meant to capture order in some sense.
Right. It's really quite easy, I think. Let me teach you how to count up to omega squared. Okay, it's totally elementary. I've taught my kids. Anybody can learn how to count to omega squared. Okay, so first of all, we're going to set aside any kind of ultrafinitist objection and so on. We're just taking on board.
Yes, by the way, this is another thing I wanted to mention. Even at the outset, in infinite, it's a game of chess. Some people, I guess, would have already objected, and I'm very curious what sort of set theory you need in order to study that.
I set all that aside. We can come back to that. Okay. Yeah. So this is how you count to omega squared. Okay, so first of all, you got to know how to count to omega. Well, everybody can count to omega because you just start 0, 1, 2, 3, 4, and so on. And maybe you say, well, how could I possibly finish counting to omega? And well, I'm not talking about doing it in time. I'm just talking about the order of the positive integers or of the non-negative integers, right? The natural numbers. And they go 0, 1, 2, 3, and so on. And for every one of them, there's the next one and so on. If you really want to count them in a finite amount of time, you could imagine saying each number more quickly, like in half the amount of time of the previous one. So that, if it takes you 1 second to say the first number and then half a second and then a quarter second and so on, then in 2 seconds, you've said all of them. Okay, so that's how you count to omega. And then what ordinal number comes after omega? The first number that comes after all those finite numbers is called omega. I mean, after all the natural numbers comes omega. That's the first infinite ordinal. And it's a limit ordinal because there's no immediately preceding number in the ordinal numbers. Okay, omega is the first limit ordinal. So we can count up to omega by just counting through all the natural numbers. And then at the end, we say omega. And that's how we count it up to omega. But of course, another thing about the ordinals is that whenever you have an ordinal, you can always add 1. And so you can go omega plus 1. And then omega plus 2, omega plus 3, omega plus 4, and so on. So there's another copy of omega sort of on top. Okay, and so what we're doing is counting up to omega plus omega. Okay, and in general, whenever you have any two orders, you can imagine another order which is obtained. It's called A plus B, and you take a copy of A and a copy of B and you put it on top. Okay, so for example, think about the way of ordering the natural numbers. You put all the even numbers first and then the odd numbers after that. I can define a linear order like that.
Yes. Well, in any case, I understand if what you mean, at least if the way I'm thinking of it is subsets of the real line. And this way of counting, that you could make a subset, going halfway, say, so
for example, if you look at the numbers 1 minus 1 over n.
Yes.
That's like a little copy of omega converging to the number 1.
Yes.
And then we put another copy, 2 minus 1 over n.
Yeah.
For any different n. Yeah.
Yes.
Together, those two sets make a copy of omega plus omega.
Now, I guess, I mean, from someone who understands cardinality, but I'm not so sure what this is meant to capture. It's like, yeah, in some sense, yes, you're adding more elements.
It's an order structure. It's a linear order. And so ordinals are about order types, about the order, not about the size. Cardinality is about equinumerosity, right? So two sets have the same cardinality if there's a bijection. Yeah, that's called equinumerosity. Yes. Yeah, that's the equinumerosity relation. But equinumerosity doesn't respect the order structure. So if I'm interested in, say, linear orders or well orders, these are actually well orders, which means that every set has the least element. Then I can't just look at the cardinality. For finite numbers, of course, cardinality and ordinality happen to be the same. Because if I have 7 elements, there's only one order with 7 elements. You put them in order, 1, 2, 3, 4, 5, 6, 7. And if I rearrange them, I've still got the same order type. So for finite cardinals and finite ordinals are basically the same thing because there's only one way to put a finite cardinal in order. But with infinite sets, that's not true, because I just described another order type for a countable set. Both omega and omega plus omega are countable ordinals. They have the same cardinality, because the evens and the odds, okay, they together make the natural numbers, so it's equinumerous with the natural numbers, but now the order type of those two order structures is not the same. They're not isomorphic as orders, even though they're bijective as sets.
I guess I don't know how I don't know if I totally understand what is required of an order, but I do understand. I guess I know what you mean. Yeah, that you could make that set 1 minus 1 over n. You could do 2 minus 1 over n. You could do, and you could keep taking unions. I suppose you could also, if you wanted, start taking those and scaling them to again. And
exactly, and that's what you basically have to do to get omega squared. Well, if I do that 3 minus 1 over n, and then 4 minus 1 over k, and 5 minus 1 over l, and so on. So I get these little copies of omega in each unit interval. You know? So I counted up to omega in the first unit interval, and then I have omega plus 1, omega plus 2, omega plus 3, and so on in the second interval. And then, so that's basically counting up to omega plus omega, which is called omega times 2. And then I have omega times 2 plus 1, omega times 2 plus 2, omega times 2 plus 3, and so on. And that's going to converge to the next limit point. And then again, I have all these different copies of omega. I can always put another one on. Altogether, I've got omega many copies of omega. That's omega squared. We just counted up to omega squared. It's just like counting to 100. How do you count to 100? Well, you count to 10 times, right? You count up to 10, and then in the teens, you're counting up to 10 again to get up to 20.
But I get to 100.
Yeah. So you
There's
get up
no
to
limit
100.
ordinals in that 100.
Yeah, okay, but I'm counting up to omega many times.
Yeah.
Okay, and also the 2-digit still makes sense, because every number along the way was omega times n plus k for some finite n and k. That's base omega. That's a 2-digit ordinal base omega. It's just like counting to 100, except it's got omega as the base instead of 10 or whatever. So just like the numbers below 100 are the 2-digit decimal numbers, the numbers below omega squared are the 2-digit base omega ordinal.
Okay, so I have her, and then I can, to go higher though, you could not, you have to change the construction that you were just doing in sort of the way I was saying, where you rescale and have to have that whole procedure maybe just to 0 and 1, and then redo it between 1 and 2. This is something I think, wasn't this introduced by Cantor? He was trying to understand possible either sets of discontinuities of Fourier series or something.
No, so the ordinals were invented by Cantor in his analysis of what's now called the Cantor-Bendixson analysis. So if you take a set of reals, maybe it has some isolated points, say a closed set. Maybe it has isolated points in it, right? So we throw those away. Okay, that's the Cantor-Bendixson process, is whenever you have a closed set, maybe if it has isolated points, you get rid of them. Now you've got a new set, and it's a closed set. Maybe you still have isolated points. How could that happen? Well, let's see. Suppose I had a convergent sequence converging to a point. So the points in the sequence are each isolated. They would get thrown out, but the limit point was not isolated. An isolated point is a point so that you can put a little neighborhood around it so that it's the only point, right? So if I had a convergent sequence converging to a point, then the points in the sequence get tossed out because they're isolated. But the limit point remains, and maybe it becomes isolated, right? So this is a set, this convergent sequence set, which is, by the way, a copy of omega plus 1. There's omega plus 1 point. So in the order topology, because we said you take 1 minus 1 over n plus the point 1 itself. That was the number omega plus 1.
Oh, 1 was the number omega plus, okay.
Right? So there's a very tight connection between these ordinals and the structure that we're talking about with these sets of reals. So if you throw out the isolated points, then maybe you have more isolated points because they weren't isolated before, but now they're isolated. And now, so you throw them out again. And then maybe you have still isolated points. So this would happen, for example, take a convergent sequence, including the limit point. And for each point on that sequence, put in a little tiny, like in the plane, imagine another sequence converging to it, but not interfering with the other sequences. Yeah? So a convergent sequence, including the limit point. And for each point on the sequence, I've got a little tiny convergent sequence converging to it. And let's think, what happens with the Cantor-Bendixson process? Okay. Well, initially, the points that are isolated are just the kind of supplemental sequences that I added, but not the main sequence, because there are limits of their supplement. Yeah. So the initially isolated points that get thrown out turn it into the convergent sequence picture. And then the isolated points from that set are the points on that sequence, but not the limit. And then what I've got is just the 1 point left, and then it gets thrown out. Okay. And so you can, and by doing that kind of thing, you can imagine now adding tertiary sequences, little tiny sequences converging to the limit points of the secondary sequences that you had added. So you can make it last one more step, and then one more step, and so on. So you can construct sets of any finite Cantor-Bendixson rank in the sense that they last n steps in the process, right? Well, can you make it last infinite steps?
I was just about to ask you that.
Yeah, well, what do you think?
What do I think? I don't know if you run into a certain problem. I only know in the real line, and I would just keep.
Yeah, that's what we're talking about, the real line, or the space,
rescaling.
the real plane. It doesn't matter really. So, okay, we said for every n, you can make it last n steps, right? So give yourself a sequence converging, and make the nth point have rank n. So when you do the Cantor-Bendixson process, after n steps, the first fewer than n points and all the sequences converging to them, that's all totally gone. But the nth point itself is left, and all the later ones. So this will be a sequence that lasts for omega many steps, a set that lasts for omega many steps. So, right, if you can handle every n, then you can also make it happen for omega many steps, because right, because you can build a sequence so that the nth one is lasting for n steps. And so no finite number of steps is going to erase everything, but omega many steps would erase everything up to the limit. So you can actually make it last omega plus 1 many steps, because the final limit point will still be there after omega many steps. You've thrown away all the earlier things, and now you've got one isolated point which gets tossed out at that stage. And so Cantor was very interested in this process, but he didn't have ordinals at first. And he needed some way of talking about what the process was. Because what does it mean to iterate the process? Well, he has a next step. The next step is always throw away the isolated points. You know, that's what the Cantor-Bendixson process is. Toss out isolated points. So you toss out isolated points and then do it again, and then do it again, and then do it again, and keep doing that forever. Well, of course, you're tossing stuff out. So it's very natural to take an intersection of what you've done. Like if you've done it for infinitely much, you want to keep what you haven't ever thrown out, which is the intersection of the sets that you have at each stage, right? And the point is that that set, it's going to be a closed set because it's an intersection of closed sets. And it might still have isolated points in it that need to be tossed out. And so you need to do it again and again. And so the structure of the stages of this construction are exactly the ordinals. That's why he invented the ordinals, to describe how to do this construction. The ordinals are very naturally the time steps of the iterations of the iteration of the Cantor-Bendixson process. And then you recognize more generally, there's a concept of transfinite recursions. This is just one instance of a transfinite recursion. You know, transfinite recursion is a transfinite sequence ordered by the ordinals, so that at each step you're doing something, and at limits, you know, you describe how to amalgamate what you've done at all the earlier stages.
Does do the ordinals interact with the cardinals in any particular way? I mean, I wonder, can you run out either of real numbers, or would you ever reach something
Right.
that's uncountable? I don't know what an uncountable ordinal would be.
Right. So if you could well order the real numbers, for example, maybe you've heard that phrase, well ordering of the reals, that would be an uncountable ordinal. The order type of that well ordering would have to be uncountable because the reals are uncountable. I mean, Cantor proved, right, that the reals are uncountable, and that more generally for any set X, the power set of X is strictly larger in terms of cardinality.
Yes.
It was kind of built into his framework that every set could be well ordered, which means that for every set, you could count it off using an ordinal, a big enough ordinal. Then if the set was uncountable, that would have to be an uncountable ordinal. Sometimes people say, well, I can't imagine what a well ordering of the reals would look like, but we can imagine the first uncountable ordinal quite easily. We can give a very concrete description of it. Namely, it's the set of countable ordinals, because any two countable ordinals are always comparable. It's a linear order, and it's a well order, and there are uncountably many countable ordinals, because if you had only countably many countable ordinals, then the union of them, the supremum of them, would be a countable union of countable sets, which is still countable. So it wouldn't be all of them. So therefore, there must be uncountably many different countable ordinals, and the smallest uncountable ordinal is just the set of them.
This is about the place I probably left off in any discussion of this, because I can appreciate that you have rules which to say this, and I guess I can sort of picture, I know what omega is, and now I can see 2 omega and maybe even omega squared, and then in principle you could do omega times that, and then you can have every polynomial omega, and maybe once you get to a higher thing, you need omega to the omega.
Right.
And,
yeah.
But
it never stops. It just keeps going.
Yeah, it's harder and harder at some point for me to connect it to a concrete problem about either analysis or subsets of the reals.
Oh, I see.
And all of this is happening well before, say, Zermelo and Frankel, right?
Yes. Yeah. This is like late 19th century Cantor. I mean, it's the start of the ordinals, sort of. I don't know the dates exactly, but 1880 something.
Can you tell me what was the impetus for what I think of as the modern conception of a set, and maybe if you could say how ordinals fit into that?
Oh, I see. You mean there's like the ZFC framework or something, or
yeah?
Okay, so Cantor, it sort of was. I mean, he's credited with inventing set theory, and he put forth his theory of ordinals and cardinals and so on. He proved the fundamental theorems about the uncountable sets and so on. But he didn't have a theory. He didn't have a first order theory. He didn't have a list of axioms that he wrote down, and that didn't come until Zermelo. I guess it was.
Can you just quickly, just to be clear, what's a first order theory and a second order?
Oh, I see. Okay, so these are concepts that come from mathematical logic, and one of the standard basic parts of mathematical logic is studying. It's called first order logic, and in first order logic we have we study theories that are expressible in a first order language, which means that they're intending to talk about first order structures, and a first order structure is of the form, you have a domain of objects like a group or an order or a field or something like that. So there's a domain of individual objects, and then there are some functions and possibly relations on those objects. So like if we think about the real field, that's a first order structure. Every real number is a point in the domain of that structure. And we have plus and times, and we have less than relation. And this is an ordered field. And the language of that structure has these two binary operations, plus and times. And maybe we have constants for 0 and 1 as officially part of the language. And then we have this binary relation of less than. And to be an ordered field, means to have certain properties that are expressible in that language. So you can say that the plus of the ordered field is an additive abelian group, and it respects the order in the sense that if you add the same thing to both sides of an inequality, then it's preserved, and so on. So this is part of the axioms, right? And then the field axioms say, well, we have times and it's associative, and every non-zero element has an additive, has a multiplicative inverse, and so on. I mean, the usual field axioms, the ordered field axioms. So that's a first order structure, and the theory of ordered fields is a first order theory because it's expressible in that kind of first order language. What the difference between first order and second order is that in a second order theory, we also allow you to quantify over arbitrary subsets of the domain and over arbitrary functions on the domain of any arity and so on. And it's a much more powerful language when you allow that kind of thing. So for example, the completeness property, the Dedekind completeness property of the real line is not first order expressible. Because what does it mean for the reals to be complete as an order? Well, we mean that every bounded set has a least upper bound. But that's a second order quantifier. I'm saying every bounded set of reals there is a real that's the least upper bound. So that's a second order statement, a second order quantifier. It's not a first. So
because you're talking about subsets?
Yes, exactly. Yeah, that's to state the least upper bound property in the real line is a second order statement, not a first order statement. But to say it's a field is a first order statement because I only need to quantify over individuals in the domain, not sets of individuals in the domain.
Okay.
Right?
I don't think
is
a distinction.
It's an extremely important difference because first order logic has all kinds of really amazing theorems that hold of it. We have compactness property, completeness property, and so on. We can prove all these things when you have a theory that's first order expressible. It means that you get to take on board the entirety of first order logic and all of the model theory that comes with that, and so on. And a lot of those things just go awry in the second order case. We don't have compactness anymore. We don't have any proof theory for second order logic. Everything gets messed up in second order logic, and it's just much less clear what's going on in the second order case.
Actually, two things come to mind now that you finally cleared up that distinction for me, which I guess I never, or either if I knew, I forgot it. One is that your description of what sort of structure you want to talk about on a set way to become first order reminds me, the way I handle those things is by talking about objects as belonging to a category. And that allows me to distinguish between what we sometimes are maybe the same object, the real numbers, but I mean the real numbers with a certain structure as an ordered field, as a topological space or whatever. And that helps me to place, oh, this is the thing I have to preserve. This is whatever. And I wonder what is the connection between some of these issues in logic and maybe even these things called models, which I don't really know what they are, and categories. And the other is that, yeah, if it makes it so much harder, I do want to talk about the subs. If I have a set, I thought I could say stuff about the subsets of that set. Is there something difficult or challenging? Do we challenge the power set axiom, or is that something that
I'm not sure I quite understand that, but I mean, of course, there's many different foundations of mathematics, so maybe we should talk about it. Set theory, of course, was perhaps maybe one of the most successful and prominent early foundations, and it was extremely important when set theory arose with Zermelo's theory, precisely because it did provide a kind of ontological foundation in which one could view the rest of mathematics as taking place inside set theory. Category theory came much later, of course, but it also is serving a kind of foundational role in that similar way, in the way that you described, that we can understand what's going on with our mathematical structures by placing them into the context of a certain category, maybe the category of sets, or maybe some other kind of category, and we can have and we can have theories that describe it. By the way, there's this the Levier theory of the elementary theory of the category of sets is a first order theory about the category of sets, and a lot of people oftentimes category theorists point to that theory as a way of using category theory as a first order theory as a foundation. And so they can take on board the power of first order logic precisely because ETCS is a first order theory. But okay, maybe you don't want to restrict, in a sense, I mean, set theory itself is a first order theory. The Zermelo-Fraenkel set theory is a first order theory. And so there's this kind of tension because, of course, whenever you want to talk about sets, then if you treat the sets as objects, right? In other words, if you augment your structure with all of the sets that are available, well, then you've put a little set theory into your structure. Then you make it a first order theory by doing that. If you treat all the sets as objects in the domain, but now your domain has a bunch of sets in it, and so really a part of your theory is set theoretic. No, right? And set theory just goes all the way and says, well, I'm going to take all the sets. That's my structure that I'm trying to axiomatize. Then it's a first order theory about sets. When I say for all X, I mean for all sets X and so on.
And that is okay, despite the fact that there is a rule that says, for any set, you can form the set of all subsets of that set.
Yeah. So the power set axiom, though, see, a model of set theory, a model of Zermelo set theory, can think it has all the subsets, but that doesn't mean it really does. It just has to have all the sets that it can, all the subsets that it can see. So, okay, so maybe I should explain it like this. One of the things about first order logic, I mentioned the compactness theorem, and it follows from the compactness theorem that we can have non-standard structures that satisfy all the same truths as the real numbers. This is the basis of non-standard analysis. So there's the hyperreal numbers, So the hyperreal numbers
is this guy, Abraham Robinson?
Yes, exactly, right? Yeah.
Okay, I have not seen yet the point of his construction, so maybe you can explain it to me.
Sure, it's extremely important because, of course, calculus was invented by Newton and Leibniz using infinitesimal numbers and so on, and it proceeded with infinitesimals for more than 100 years. And of course,
I think bad language. I feel like Newton did understand limits, but maybe that's just my own reading of his psychology.
He talked a lot about infinitesimals and so on in a way that I think
people talked about it.
You wouldn't, right?
And then this Bishop Berkeley really harped on this a whole lot. Right. I feel he didn't really understand calculus.
Shall we not call them the ghosts of departed quantities? That's the famous quote from Berkeley, and sort of mocking the treatment of infinitesimals. And I think Berkeley's point is right on, that the foundations were quite insecure. They weren't properly explained. And it really, in the 19th century, of course, with the Weierstrass and the epsilon delta account, then finally calculus was on a rigorous foundation and so on. But in the 1950s, Robinson developed non-standard analysis, and he proved, look, there's a completely rigorous way to do calculus with infinitesimals because we have these hyperreals. And what are the hyperreals? The hyperreals are an ordered field, and they contain the real numbers as a subfield. But the hyperreals have numbers, let's call it one of them epsilon. And epsilon is positive, but it's less than a half, and it's less than a third, and it's less than a fourth, and so on. It's less than 1 over n. It's less than 1 over n for every positive integer n. So it's infinitesimal, but it's in the hyperreal field. It's a positive element. So there's these little infinitesimal numbers that are smaller than every positive real number in the hyperreal numbers. But the most important thing about the hyperreals is that they satisfy the same theory. Any statement that's true in the real numbers is also, any first order statement that's true in the language of the real numbers is also true in the hyperreals. So whatever statement you want, namely that some connection, some algebraic equation or whatever, it still works exactly like that in the hyperreals because of this transfer principle. We can transfer truths from the reals to the hyperreals.
But they must be different somehow.
Well, there's more. There are these infinitesimal ones, and their reciprocals are infinite. They're bigger than every integer. And so it follows that for example, the hyperreals cannot have the least upper bound property because the reals are inside the hyperreals, but there can't be a least upper bound for them because if you subtracted 1 from that number, it would still be bigger than that. So therefore, the hyperreals cannot be Dedekind complete. You know, they won't have the completeness property of the reals, but that just shows, that's a proof that the completeness property is not first order expressible.
Okay, I see that. That makes sense.
Yeah. So if you want to talk about all subsets and so on, the second order thing, okay, then you're not doing non-standard analysis. So non-standard analysis, I view it as a kind of amazing development. It's a joke that mathematical reality has played on us all, because of course the story that we all knew, you know, before Robinson was Newton and Leibniz had infinitesimals, but those foundations were possibly flawed and shaky, and finally it was on a rigorous footing with epsilon deltas. But then non-standard analysis shows no, it was actually fine to use infinitesimals. You know, of course, what Robinson is doing isn't the same as what Newton and Leibniz is doing, and it's much more subtle and refined and so on. But nevertheless, it shows that the basic idea of using infinitesimals can be done, you know, pretty close to how they were talking about it.
I guess I have my own sense of this story that doesn't really intersect with set theory, that, you know, there were foundations that might have been appropriate for talking about convergent power series if that was all calculus was supposed to look at. That would have been okay. And that once Fourier series were introduced and that didn't align with what was expected of power series, you needed to go back and understand these questions about limits and the real numbers that these people didn't have to have. And I think Robinson's construction is totally different from what anything Newton or Leibniz had in mind. But what I'm okay, that I guess I see what this illustrates in the world of logic. But I'm still on the set theory and its beginning, because it's these it's some of these axioms in the Zermelo-Fraenkel theory are controversial, and I want to know which ones and what how these things come up. So right. So maybe you could, what were they doing? How did they write down these axioms of set theory, and what do these things mean for either just set theory or all of mathematics? Right.
Okay, so let me explain a little about how the ZFC axioms came to be. So Zermelo proved the well-ordered theorem that the reals are well-orderable. What does it mean to be well-ordered? I mean, of course, the real order itself, the reals already have an order, the usual order on the real line. But that's not a well-order. A well-order is an order that makes it like an ordinal, so that every set has at least element. Okay, there's always a next, and then a next, and a next, and at limits, and then a next. So that's the fundamental nature of well-order. The definition is that it's a linear order so that every set has a least element. Well orders are orders so that you can do induction, because if you want to show it's true for everybody, but if it's not true for somebody, then there's a least point where it fails, and that least point where it fails, like when you're doing ordinary induction on the natural numbers, the essence of it is that there aren't any minimal counterexamples, right? There's no minimal place where it becomes false, because that's exactly what would violate, whether you're using strong induction or weak induction or whatever, it's all boiling down to the fact that there's no minimal counterexample. And well orders are a kind of way of extending that beyond just omega into the ordinals. It's the same idea. And so the question is there a well ordering of the real numbers? Can we put the real numbers into a well order? And it's hard to imagine what this order would be like. And Zermelo proved there was one, but people didn't like his proof. And it wasn't clear maybe exactly what the assumptions were, because he's proving it in set theory, but there was no set theory. There's no official, at that time, there wasn't any list of axioms. And so he said, okay, and he wrote down a list of axioms about what he needed, and those were the Zermelo axioms of set theory. And then he proved from those axioms that the reals have a well order. But one of his axioms was called the axiom of choice, which says that whenever you have a bunch of non-empty sets, for any set of non-empty sets, there's a function that picks an element from each of them. A function that you give it the set, it gives you an element of the set. So f of a is an element of a for every a in the family. Okay. It's sort of obvious. I mean, I view the axiom of choice as obvious. That's what we want for set theory. Of course, if we think that there are sets and all different kinds of sets, then of course there should be such a choice function, because we're trying to, we're writing down axioms about what sets there are, and their sets come in all kinds of diverse possibilities and patterns and so on. And so all I want is that there is some set that makes these choices for every element of the family. And I think Zermelo thought also that it was a kind of obvious axiom. And from that axiom, he could prove that the reals have a well. Let me show you how to prove it. Actually, it's quite easy to make a well ordering of the real numbers. We just do it like this. We take all the non-empty sets of reals and we fix a choice function on that family. So whenever you have any non-empty set of reals, the choice function gives you one of them from that set. Okay. So if I apply that function to the whole set of reals, it's going to give me a real number. Because that it's picking an element from every non-empty set of real numbers. The choice function picks one. Okay, so it's going to pick one from the whole set. I'm going to put that at the bottom of the order. And now I look at the set of things that are remaining.
Yeah.
And the choice function picks one, so I put that one next. And now I throw those two numbers out. I've got almost all the reals except for those two. The choice function picks one of what's left. I put that one next, and so on. And I just keep doing that forever. That's the well order. That's how you prove that if the axiom of choice holds, then every set has a well order. And it's very natural. It's just, you just pick one. It doesn't matter which one you pick. I mean, in a sense, that's the philosophical attitude about it also, is that the well order just comes from picking amongst the numbers that are left. And if you just iterate that, you get a well order. And so it doesn't matter how you picked, you're going to get a well order. Of course, different ways of picking are going to give you different well orders, but somehow, and so we expect maybe a lot of different well orders, because we also expect a lot of different ways of picking from those sets. And so
I suspect this is where some people begin to have objections. It's like on the one hand, it seems that it should be obvious, yes, in what you described, every time you have a remaining set, there's got to be some element from it. Of course, it's non-empty. And yet, on the other hand, this is the objection. Well, if something is not computable, if you couldn't put it, you don't have a way of producing it,
right, then
should we admit that construction?
Right, I see. So this is maybe getting into these ultra-finitist ideas that you had mentioned earlier. Right.
Well, I'm not sure that they're the only ones who've put forward that objection. I guess he was objecting. I know there's a bunch of these axioms of set theory, and some of them seem like the kinds of things that I think, I think of them as like the definition of a set. Is that the right way of thinking? I think of it as, well,
you're right to say, look, the axiom of choice has a fundamentally different character from many of the other axioms, because the other axioms of set theory are saying, are defining, they're asserting set existence for particular sets with defining properties, and they're only one, like the power set, or the union set, or the empty set, or the set omega, and so on, a set of stuff. But the axiom of choice is not saying a particular one. It's just saying, look, there's some way of choosing, maybe a lot of different ways. Yeah.
Well, it seems that I just want to say, it seems like which of these axioms are controversial. It seems like some people are already disagreeing with that there exists an infinite set, that you had to allow that. You couldn't. It somehow didn't follow from the earlier ones, just from the existence of finite sets, that you could just that they. I mean, it seems to me very natural. You can talk about all the natural numbers at once, and that's a thing that we'd want to talk about, and yet it doesn't fit in there. And then you get it. So it's like, that's the first, maybe I didn't realize people thought that was controversial until I heard from this guy, Norman. And I always knew, I guess, hearing from the lore of mathematics, that this axiom of choice was controversial to some people, and that they wanted to, separate out which results depend on the axiom of choice and which don't. And, as an analyst, I love the Arzela-Ascoli theorem, and I believe that does use the axiom of choice. And of course, I've seen these constructions of non-measurable sets, and whatever. And I'm happy to have that. And we just be careful about our theory of measure handles only these kinds of sets,
Right.
and
Right.
that's fine with me. But I never went beyond. So these are the things that we get into what I believe are the controversies. I don't know if this gets into more modern stuff, but like infinity, choice.
So you should also
continuum
mention the
hypothesis.
replacement axiom, though. So the rest of the Zermelo story is that Zermelo didn't include what's called the replacement axiom. That's the axiom that says if you have a set and everybody in that set has a unique witness of something, some property, then you should be able to collect those witnesses together and make a set. So in other words, you probably use this axiom all the time without thinking about it. Suppose for every natural number n, you can define a certain object a sub n. Then you should be able to make the set of the a sub n's. That's the replacement axiom. That's an instance of the replacement axiom. It says, if you have a set already and everybody in the set has a unique thing that you're defining from it, then you can collect those things together into a set. That's replacement.
So this is like, you can give it in terms of like functional property, having already defined functions as like some subset of the product set, or with
but this would be a definable, a class function. So if you can define something that would be a function if it existed, then it does exist if the domain is already a set. Yeah. And so this is an axiom that, okay, Zermelo didn't include it, but then later set theorists observed, look, we can't prove that the set of the Aleph n's exists. For every natural number n, we can define the cardinality Aleph sub n. But if you don't have replacement, you can't put those together into a set. And the set theorists, of course, wanted to put them into a set because then we make Aleph sub omega and so on and keep going. And so it was Frankel that observed that we need replacement in order to do this kind of basic form of reasoning in set theory. And so when you add replacement, then it becomes the Zermelo-Frankel axioms.
Just to make sure I know, the Aleph sub n's, Aleph null is the cardinality of the natural numbers.
Yes.
And this order is Aleph sub n. What is that? The next.
So Aleph 1 is the first ordinal that's not equinumerous with the previous one. So Aleph 1 is the cardinality of the first uncountable ordinal, and Aleph 2 is the cardinality of the next one, and so on. So the continuum hypothesis, for example, Cantor was obsessed with the continuum hypothesis, which is the assertion that Aleph 1 is the same thing as the cardinality of the real numbers. But that turns out, we only know much later, not to be provable in ZFC. Either way, it's independent. So it was quite. So Gödel had proved in 1938 that it was consistent that the continuum hypothesis and the axiom of choice are true with ZF. And Cohen proved in 1962 that the negations are also consistent using the method of forcing. So this was really quite dramatic and powerful tools that were added at that time.
I see. So my question is how to look at this. Like, is it that there is some definition, there is something that's a set that's the thing we want to talk about, or they're just different types of sets, and each belongs, I can imagine there's a category of sets following this definition and a category of sets following some other set of definitions where other things are allowed. I don't know if this lines up with you've used these words that is not part of my logic education models, and you just mentioned forcing, which I've tried to look into a little bit of what that is in preparation for this conversation, but I guess I don't know exactly. I wonder if these are.
Well, let me say a little about it then.
Yeah.
So, okay. So, how do you show that an axiom can't be proved from a theorem, from a theory? Like, for example, how do we know that the parallel postulate can't be proved from the other axioms of geometry, the other Euclidean axioms? Well, if you could exhibit
a thing that satisfies the other.
A model.
A model? Okay.
Yeah, if you can exhibit a model where the theory is true, but the statement is not, then it doesn't follow from the theory, right?
Yeah.
So to show that something is independent of a theory, you have to show two models. You have to show a model of the theory, one model where the statement is true, and another model of the theory where the statement is false. And then you can't prove it or the negation. How do you know? Let's say in group theory, how do we know the abelian axiom? I mean, I can imagine the abelian axiom. It's asserting commutativity of the group, right? AB equals BA for every AB. How do I know that's independent of group theory? Well, because I can give you a group where it's true, and I can give you another group where it's not true, right? So that means we can't prove or refute the abelian axiom from the other axioms of group theory, from what it means to be a group.
Yeah.
Similarly, we can't prove or refute the parallel postulate in geometry because we have geometries, where it goes both ways. There's non-Euclidean and Euclidean. So if you look at set theory, there's just hundreds and hundreds of independent statements like this. So the continuum hypothesis is independent of the other axioms of set theory because there are models of ZFC in which the continuum hypothesis is true. That's what Gödel had provided in 1938. And there are other models of ZFC in which the continuum hypothesis is false. This is what Cohen had provided in 1962. And the way that Cohen did it was fascinating because he invented this method called forcing, which is a very powerful way of taking any model of set theory and producing another model, an extension of it, a forcing extension. In algebra, we can talk about field extensions of the rational field, algebraic or transcendental field extensions. And the way that you make an extension is you add this new kind of ideal object that obeys an algebraic equation or doesn't satisfy any algebraic equation and so on for those two cases, right? And in set theory, there's something very similar. You can take any model of set theory of ZFC and you can add what's called a generic object, a generic filter for a certain forcing notion, which is a partial order in the model. And every object in the forcing extension can be constructed concretely from objects you already had and this new ideal object, just like in a field extension case. So it somehow generates the extension. But it does so in a way that you can often control and predict what the truths of the forcing extension will be. This is the real power of the method, is that we can calculate the truths of the forcing extension on the basis of the nature of this partial order. And so we can make the continuum hypothesis true, or we can make it false by going to a forcing extension. So it's what's called a switch in my analysis of the modal logic of forcing. The continuum hypothesis is a switch in the sense that you can turn it on and off by going more and more forcing. You can always find another forcing extension where it's true, a bigger one where it's false, another one where it's true, and so on. You can turn it on and off as much as you like. And there's a lot of statements like that. It's in contrast to other statements that we can make where they're not true yet, but if you go to a forcing extension, they become true, and then they stay true in all further extensions. So these are called buttons because you push the button and it stays pushed. You can't unpush it.
I guess, okay, I think I understand, you add something in, I guess I don't know what a filter is exactly, but you add something in with the property that makes it have the thing that you want. Then you have to see what other things have to belong there to fit all the other
exactly, because if you have that
rules.
New set, you also have its singleton and the power set and its union with all the other sets and so on. You generate all those new things that have to be there because you have a model of set theory, and that altogether, that makes the forcing extension.
Is a model, okay, this is my curiosity, that really does sound to me a lot like the idea of a category of things that preserve a certain kind of structure. Is there maybe they're completely different? I don't know, but
well, there are category theoretic accounts of forcing. I mean, coming from topos theory and so on. But in my experience, there's a genuine difficulty translating between the set theoretic realm and the category theoretic realm, in that even very elementary and easy concepts have an analog in the other realm, but it's extremely difficult to say exactly what they are. And And what the world needs is people who maybe are trained in both of these areas to translate back and forth.
That's what the world needs. What's a set versus a class? Something
okay.
I've heard of, because
Right.
in category theory they're like, well, all these categories. I'm very happy to talk about structure in the abstract, and yet there is no set of things with that structure. And now
Right.
I'm realizing, the way I'm talking about that's somehow not well defined. When I think of something
Okay.
being well defined, it's a set, but it's not a set. What is that? What's
Okay,
happening here?
let me start with one of the most basic things you can do in set theory is if you have some property and you want to make the set of all X that have that property. Yeah, that's what you do when you're using set theory. Okay, so let's take that as an axiom. It's called the general comprehension axiom, and it says for any property whatsoever that's expressible, you can make the set of all X such that phi of X, where phi is the property that you have. Yeah.
And is that the thing that runs into the Russell's paradox? Or
exactly. This principle is just wrong. It's self-contradictory in one line, namely, let R be the set of all, R standing for Russell, let R be the set of all X such that X is not an element of X. And then you just observe, well, is R in that set? R, in other words, is R an element of R? Well, if it were, then it shouldn't be, because R was the set of of X that weren't members of themselves. So R is in R if and only if R is not in R. That's just a contradiction. Okay. So this is a refutation of the general comprehension axiom, Russell's refutation, destroying Frege's system that in which the general comprehension axiom had been an implicit part. Okay, but the point is that even though it's not a set, we still can talk about the collection of X's with property phi, whether or not it's a set, right? That's a class. A class is a collection of objects. Maybe it's a huge collection and it's too big to be a set because of the Russell paradox kind of thing. But still we can talk about having property phi. So a class is, some set theorists don't like to talk about classes as objects. They say, no, it's just a shorthand way for saying that the particular X that you have has the certain property phi. Yeah. So to say that X is in that class is just a kind of synonymous way of saying that X has property phi, which is perfectly fine. If phi is an expressible property, then you can say that X has property phi. It doesn't mean you're committing yourself ontologically to the existence of this object that is the class, right? Okay, but meanwhile, there's other class theories that develop where the classes are actually objects in the structure and so on. They're not sets, but not necessarily sets. Maybe I should say, oh, go ahead.
Well, it's very hard to know what we're talking about if you can't say definitively whether a thing is it or not. Is that the issue with a class?
Maybe. So, right. Okay, let me describe when you're writing down the axioms of set theory, so when you're trying to axiomatize what it is that you're talking about, then what is this realm of sets? What is it like? And the picture that you should have is, well, maybe you have some what are called elements, these atoms that aren't sets, but they're fundamental objects of some kind. Maybe you have some, I mean, historically it was traditional to have these kind of elements or atoms, And then that's the kind of bottom level. And then you can maybe imagine, well, I want to take all sets of those things, okay? And those exist on the next level. Sets of elements are on the next level, And then, okay, well, I've just added a bunch of new objects. This is called the cumulative hierarchy, by the way. I've added a bunch of new objects. Now I want to take all sets of those things together with the earlier things. That's another layer, yeah.
Is there anything in particular you're conceiving as what those elements are? I guess I'm not.
No, in fact, in the contemporary way of approaching set theory, we've recognized that we don't need any elements at all, and so there aren't any.
Okay.
But traditionally, maybe people thought, well, we need elements for the numbers because what's a number anyways? And maybe I want to take natural numbers as kind of atomic things that I'm going to do set theory on top of. Yeah. Or maybe the elements are like the points in the Euclidean space or something, because you want to take those as atomic objects and do set theory using sets of points in space and sets of points and so on. And so I think that's the attitude that people have. There might be some mathematically atomic objects that we want to put into our theory and do set theory on top of it. Yeah. But nowadays we recognize actually we don't need any elements, and we get a perfectly satisfactory theory without any elements. And it's somehow conceptually cleaner and nicer and conforms maybe closer with the philosophy of structuralism to not have any elements. And so generally we don't have any elements now. But okay, a lot of people want to have them, so let me imagine that we have them. Then we take sets of elements and sets of elements and sets of elements and so on. And we gradually are building up this universe of sets that exist. Yeah. So at every stage, the sets that come into existence are the sets that consist of earlier things that had already come into existence. And this is a picture of how the set theoretic universe grows. You know? And if you have that picture, then you shouldn't believe in general comprehension, because the whole set theoretic universe is what you get after you've finished this whole process forever. And I don't just mean at finite stages, I mean going through all the ordinals. But then the collection of all x such that phi of x, well, if those x's had arrived unboundedly in the hierarchy, there was no stage at which you had them all, and so you never got the set. That's what a proper class is. That's the picture that you should have for a proper class. A proper class had objects that appeared at later and later stages in the cumulative hierarchy, and that's why it's not existing as a set, because there was never any stage where you had them all. So for example, the Russell class, the set of all non-self-membered sets. I mean, on this cumulative picture, we never expect the set X to be an element of X, because a set would appear, then all of its elements were already there earlier. So X is never an element of X on this picture. So therefore the Russell set is everything. But you also never have any stage where you already had everything, because there's a next stage after.
Interesting. Okay, I've not heard that that resolution of this issue before. I guess
so the point is that this cumulative hierarchy picture, which I think is it's the way that we can understand what is it we're trying to do with the axiomatic set theory. We're trying to axiomatize this picture, and the point is that that picture offers no support whatsoever for the general comprehension principle. The general comprehension principle is a kind of logical error. It's like denying the antecedent or some kind of logical fallacy. We should really have there's no residual support that we should have, because it seems like it should really be true, even though it's refuted in one line.
Does this require these axioms of higher infinities to do? Do you need to keep putting in more rules so that you can talk? You need to complete, if you start from the smaller constructions, you needed that first axiom infinity, right. Then you need another one or another one, or is
right. So in the Zermelo theory, you can't prove that this V alpha hierarchy, this cumulative hierarchy, exists where every level is a stage, every stage is a set. And also it's kind of built in, if the next layer is a set, the set of all things that you could add, then this is implying the power set axiom. Because whenever you had a set, then you also have all of its subsets already. And so the power set is existing at the next stage. So there's certain aspects of the picture that lead you to certain axioms in the theory. And of course, once you have power set axiom, then by Cantor's theorem, you're going to be committed to these increasingly large infinities. And then it's a question of, how tall is the cumulative hierarchy? How long do these ordinals last? And different set theories can have different answers on that. Some of the weaker set theories say if you drop the power set axiom, then you don't get that the levels of the cumulative hierarchy are sets. They might already be proper classes. And that's quite an interesting situation.
Well, maybe I just wear your philosopher hat for just a moment to
Sure, I'm happy to.
entertain my maybe a ill-formed question. I'm just thinking when we use words or try to explain what we mean to people, I'm just wondering whether we are referring to sets, a mathematical objects. I typically think, it has to belong to some set. I have to be able to say whether something is that or isn't it. But I feel like in our language, oftentimes the way we understand a thing is somehow more nebulous from its properties. It's built up in some other way. And I wonder if there's a way of connecting either the category or class concept to this somehow more nebulous understanding of, I don't know, the way we use words in our language. What's a chair, or what's red? I haven't thought this through, so
I'm not sure I'm following the question. I'm sorry.
Well, I'm just thinking that there is no set. It is not clear what is the membership in that property. That some of the terms that we name, and yet we understand it by its relation to maybe some other things. I'm just trying to see if the notion of what is a group. We know it by its properties.
Right.
There is we have this collection of properties by which we say this is a mathematical object called a group, but we can't say what the set of all groups. I'm wondering if which concept maps more neatly onto our language, because the next thing that I want to get to is which version of set theory or what set of foundations maps more neatly onto the kinds of mathematics that people actually practice. But
right.
I'm just wondering if there's any if anyone has any resolution.
So there's a kind of connection, between some of the things that you mentioned, namely this kind of cumulative hierarchy picture. Of course, there might be some stages where if we look at all the sets we build up to that stage, maybe it looks great. Maybe in that model, all the axioms of ZFC maybe could be true before we get to the top. And when that happens, it's called a universe. So maybe in category theory they use universes. And the category theoretic concept, a Grothendieck universe, or I call them Zermelo-Grothendieck universe because Zermelo was looking at them many decades earlier. And these are exactly the stages in this cumulative hierarchy that are chopped off so as to satisfy the second order Zermelo-Frankel axioms. So that's what a Grothendieck universe is. It's exactly an initial segment of the hierarchy that already satisfies set theory. And maybe there's a lot of them. And so this kind of picture of the set theoretic universe growing, but having stages that look like perfectly good universes along the way, I think resonates very much with what category theorists have to do. And of course, what they're doing with the universe axiom and universes. And the move that you make in category theory when you have to, you don't take the category of all groups, you take the category of, U small groups for some universe U, which means that the groups are in that universe. But every once in a while, you want to look at functors from that category to something else. And so the context is getting bigger. And so you move to the next universe and so on. And the reason why that has to happen in category theory is precisely because of the Russell paradox. And the introduction of the universes into category theory is exactly solving this problem that not all classes are sets. But when you have a restricted form of the universe, then the things that look like classes in that universe are actually sets in the real universe or in the next universe, if you want. Because, if I have a universe and I build its Russell class, it's not a set in that universe, but it's added at the next stage because it's a subset of the things that exist in that universe. And so it's a way of kind of jumping out of the problems that's caused by Russell. And so there's actually, I think, a quite tight connection between the way universes are used in category theory and Zermelo's picture of the cumulative hierarchy with these significant stages that count as universes.
Okay, I mean, I think I can believe that the way that you construct something and see how some statement is independent of the other statements, and how something might be true in one universe and not true in another place. But now I wonder, how do you make any kinds of decisions? Somehow, I don't think people will be satisfied by saying, well, there's any, you can take, maybe not any, but lots of different perspectives on these things, or potentially, especially when people think of these things as foundations for their subject. And I'm very curious as to how, or certainly on what basis even, you make decisions or make definite, theorems within this subject, other than these independence results. How do you come down some way definitively on, I don't know, on the continuum hypothesis or something like that? And I'm especially interested, maybe, I mean, this may not be the way you go, but maybe where does it interact with some other mathematics? What would be the are there consequences there?
Oh, I see. Okay, so there's extremely rich answer to these questions. So let me just say some things. Okay, there's a kind of fundamental dichotomy in the philosophy of set theory between what's called the singularist view or the universe view and the multiverse view or pluralist view. And that is, when we're describing this cumulative set theoretic universe, is there just one? Is there the one true set theoretic universe? And then when you ask, well, what's true in set theory, you're really asking what's true in that one true universe. So this is the universalist view. And then there's the multiverse view or pluralist view that holds that, well, actually, there are many different concepts of set, and they each give rise to their own kind of universe, not necessarily just in this universe manner of chopping off, but maybe they can even differ on fundamental statements down low. There are fundamentally different conceptions of set giving rise to fundamentally different cumulative hierarchies. Okay, and these different perspectives lead you to different ways of answering that question about how do we find out what's really true? How do we find out what whether the continuum hypothesis is true or not true, and so on. And if you're a universalist, then the mathematical program that you're going to be following is trying to find out what's true in the one true universe. Is CH true or is not CH true? And it's hard to imagine exactly how you should go about that. What's the criteria by which you should add one axiom or another? And people provide different criteria. So, for example, there's the large cardinal hierarchy is the strongest known axioms in mathematics are asserting the existence of these extremely strong infinities. And it turns out to be quite interesting. They have these fascinating and remarkable consequences down low. The existence of these huge infinities has consequences even for sets of real numbers. I mean, to give one example, if you take a closed set in R3 in 3 space, and project it to one of the planes, one of the axis planes, and then in that plane take the complement and project it to one of the axis lines, you get a set of real numbers that way. So we started with a closed set, we project, complement, project again. So we get a set of reals. Is it Lebesgue measurable? So one can ask, is it Lebesgue measurable? Okay. It turns out you can't prove that in ZFC. It's independent. But if there are large cardinals, it's just true. It is. It's Lebesgue measurable. So this is an instance where observable properties, I mean, we can take particular closed sets like definable sets by some property, and in every case, we always observe it's Lebesgue measurable. So So in a sense, it's a kind of scientific experiment. It's positive support. The fact that that we observe that in fact all those sets when they arise are Lebesgue measurable is evidence that there are large cardinals. I mean, on a thinking about the matter in terms of like scientific evidence, because it's just a consequence that if there are these large cardinals, then in fact every projective set of reals, so every set of reals that you can define by quantifying over the reals, that's what projection is. It's asking, is there an X such that, right? And so the set of reals that arise from any dimension, doing that and taking complements, it's like doing logic, right? Taking the complement as negation and so on. And the projective sets are exactly the sets that arise by that kind of process. And if there are these huge infinities, then it turns out that all those sets are Lebesgue measurable and have the property of Baire. They differ from an open set by a meager set, and all these beautiful regularity properties. And those are properties that we observe in every case. When we know the answer, it always comes out like that. Yeah, they are. They do have the regularity properties. So this is extrinsic support.
I see. So you need these large cardinals even to say, I guess I did see a little bit about this. People ask, what size set do you need? What's the small set that is not null with respect to Lebesgue measure?
Yeah, for example, this is one of the things that's independent. So, I mean, of course, the Lebesgue measure is countably additive, but could it be more than that?
Yeah.
Well, of course, we can add up continuum many singletons, and that's going to be the full set. So if CH holds, then it can't be more than countably additive. But if CH fails, there's a lot of infinite numbers in between, and maybe it can be a little bit additive. And it's known to be consistent with ZFC that it's less than continuum additive. So you can always add omega 1 many or omega 2 many if those are less than the continuum.
And you're saying with the large cardinals, you can give a construction of these sets in between, but if you don't have the large cardinal, you can't. Or
unfortunately, it's not like that, because the large cardinals don't settle CH. But the point is that the large cardinals are implying that if you can easily define the set of reals, then it's going to be measurable and have property of Baire and so on. And that's something that's not at all obvious. We don't know any way to prove that in general. And in fact, it's independent of ZFC, those statements. And it's false in Gödel's model. So if for example, there were an easily definable well ordering of the reals, then it would contradict those conclusions. Because you could take that well ordering and use it to build a non-measurable set and so on, and the complexity wouldn't go up that much. And so if you had a definable well ordering, and it's consistent that there is a definable well ordering. A lot of people say, oh, axiom of choice means that you're making arbitrary choices that cannot in principle be definable. But that's not a correct understanding of the axiom of choice, because it's actually consistent with the axioms of set theory that there's a definable choice function, at level of delta 1, 2.
Yeah, I don't know what that means, but
so it's pretty low in the complexity hierarchy I'm talking about. It would be arised as, for example, take a closed set in R3 and project and complement and project and so on. You could get something that's coding a well ordering of the reals that way. And so from that well ordering, you can build non-Lebesgue measurable sets and so on. So that just proves that there can't be any large cardinals, any of those enormous large cardinals in Gödel's universe where this definable well ordering exists. So Scott famously proved that there's no measurable cardinals in L. So under the axiom of constructibility, which is Gödel's model, there aren't any measurable cardinals. There can be still Grothendieck universes and so on, and you can go up quite a long way, weakly compact and so on. But at a certain level in the large cardinal hierarchy, you can't have them consistently with V equal L anymore with Gödel's universe. And so these large cardinals are having these beautiful and very welcome consequences for sets of reals. And they're also implying that the cumulative universe is very fat. It has a lot of reals and it's not constructible and so on. So
this is something I've heard of, and I'm a little bit afraid to ask what is V and what is L. because I think that could take us, that might take us a long
It's not
time.
so hard. V
Oh,
is the cumulative hierarchy. That's what we've been
okay,
talking about.
okay,
That's
okay.
V. And L is Gödel's model. It's called the constructible universe. And it's the model in which Gödel used in 1938 to prove that the continuum hypothesis and the axiom of choice are consistent with the other axioms of set theory. It's sort of like, it's like this. So we said, I described how to make the cumulative hierarchy, where at every stage you add all the sets that you could that consist of earlier ones. In Gödel's model, it also has a hierarchy, and at each stage, you only add the sets that you can define amongst what you already had. So it's iterating not the power set, but it's iterating the definable power set. So you add in the things that you have to have. It's a kind of minimal, you add as little as possible, And it turns out if you do that at every stage, you get a model of ZF, of a set of C plus the continuum hypothesis. It's quite amazing. And so that's L. L is iterating the definable power set operation, and V is iterating the power set operation.
Okay. I don't know if that maps exactly onto the kinds of issues that that Norman brought up, but it's somehow analogous, I feel, because he wants to restrict to definable might be different from computable and all these other things of algorithm and whatever. But that I know that these people want to make some kind of restriction. I very curious. Is there a I don't know if you're familiar with that world of ultra-finitism or something.
Sure.
What would that what would the conclusion be? What would that world look like? I'm sort of curious.
Right. Okay. I mean, I guess what I would say is there's a lot of different philosophies of mathematics. I mean, we have Platonism, and I already described the sort of singularist Platonism and plural Platonism.
I think of that as being, very philosophical, somehow not touching.
And then there's, formalism and fictionalism and structuralism and logicism and ultrafinitism and skepticism and so on. And in each of these philosophies, I mean, for the most part, the philosophical explanation that you're giving about what's going on often is compatible with the very same mathematics. If you think about, say, what is the formalist account of proving some theorem versus what is the Platonist account? If I prove a theorem in set theory, then maybe the Platonist would say, yeah, he's proving that the reals are uncountable and there's this actual set of reals and it's uncountable, there's no enumeration of it and so on. And the formalist would say, well, he proved the following statement and then give me the formal symbols of that statement. And the proof was this sequence of statements which obey the rules of deduction for the proof system and so on. And so the formalist can say, can give his explanation or her explanation of what happened mathematically. So it's the same mathematics in each case, but the philosophical interpretation of what happened is quite different. So for the formalist, there's no commitment to the existence of any infinite objects whatsoever, and the only thing that we're talking about are the sequences of symbols and the statements themselves and so on, and whether or not they were manipulated according to the formal rules of the proof system and so on. This is a kind of formalist way of understanding it. But the point is that the argument was exactly the same, the mathematical argument. Yeah, okay. And so one is led to the question, so in that sense, there's often little at stake mathematically when you change the philosophical perspective. And so what one is led to maybe is wondering, well, what is the philosophical position for? And one way of answering that question is that these different philosophies of mathematics are to be, or give rise to different mathematical questions and programs and problems. So if you're a multiverse Platonist, then you're going to be led to mathematical questions that are about relating these different universes and how can this universe relate to that one by forcing or ultra power or the category of all universes and maps between them or questions like that. But if you're a universe Platonist, then you're going to be led to questions about, well, how can I find out whether the CH is really true or not, and what could be the grounds for deciding that, and so on. Or if you're a formalist, then you're going to be led to questions about what is the nature of mathematical reasoning, and what is the best language to be using, and what are the deductive steps that should be allowed, and so on. Or if you're a fictionalist is someone who thinks that the status of mathematical statements is similar to the status of stories about fictional events. So if I make a statement about, say, in the Beatrix Potter story about Jeremy Fisher, the frog, the talking frog, he likes to go punting, he goes boating and fishing and so on. Okay, so it's true in the story that Jeremy Fisher can talk and he likes to go boating.
I don't know that story. Wait, who's Beatrix Potter? Is that
the Peter Rabbit? Yeah.
Okay,
so one of her books. It's for children, right? I highly recommend. Yeah, Jeremy Fisher. He's a frog. He goes punting and boating, and he has an adventure catching a giant fish and so on. Okay, but there isn't any talking frog actually, and so if I say Jeremy Fisher enjoys punting, then the status of that statement is what it really means is something like, according to the story of Beatrix Potter, Jeremy Fisher enjoys punting. And so a mathematical fictionalist would say the status of mathematical claims is something like that. According to the Peano axioms of arithmetic, there are infinitely many primes. I'm not saying there actually are infinitely many primes. I mean, a fictionalist isn't actually saying that. He's just saying, according to the story, according to that theory, it's true. You know? So if you're a fictionalist, then fictionalism is really about the interplay of the object theory and the meta theory, right? Because that the status of the assertions is saying, well, according to the theory, this statement is true. And so we have these kind of two realms of assertions that are taking place. So my point is that these different philosophical positions lead you to different kinds of mathematics. And I think it's reasonable to say that the philosophical positions might be judged by the mathematical value and the insight that those mathematical programs, you know, the resulting mathematics.
Oh, wait, so can you say again, because in the beginning, I followed you and I was about to be very, I don't like the philosophy when it leads to the same thing, you're just putting it in some different language, but now you're saying, but what, can you say again, what really would be the difference?
So that what I'm saying is that in many cases, the philosophical position doesn't seem to affect the mathematics, it's sort of, right? But, and this is the important part, the different philosophical perspectives lead you to want to do different kinds of mathematics. And we can judge the philosophical position by the value of those mathematical programs. And do they lead to deep insights and new knowledge? And do we understand things better as a result? Yeah. And so if, for example, if one is a skeptic, yeah, I mean, a hardcore skeptic, you know, infinite sets don't exist and probably 10 to the 100 doesn't exist and so on, this kind of thing. Yeah. If the content of the philosophical position is just pure skepticism, okay, I'm not saying that there's anyone like that with that view. Ultrafinitists aren't necessarily skeptics in that way. Yeah, there's other kinds. So the skeptical view seems not to lead to very much interesting mathematics at all. And in that sense, I mean, of course, it's easy to be a skeptic about anything, and it doesn't tell you what you should look at or what kind of mathematics you should look at. Okay, so a richer form of ultrafinitism isn't just skeptical and rejecting these huge mathematical programs that are hugely successful and have led to extremely rich mathematical theories by which we've learned a lot. It's not just rejecting those, but rather if your philosophy of ultrafinitism is leading you to concentrate on sort of finite combinatorial questions or computability issues and so on, then that can be very rich. And we can say, yeah, that's a good philosophy to have because it led you to want to, you know, look at complexity of algorithms and so on, and to efficient computation of these very tractable problems and so on. And it can be completely fine on those grounds, right? And so I would say that, yeah, so the main point that I'm trying to make is that we can judge these philosophical positions We don't have to judge them on the basis of philosophical truth, because in a sense, they're all compatible with the mathematics. We can judge them on the basis of the mathematics to which they give rise. As mathematicians, we can make that judgment. And those are often very interesting, I think.
Yeah, that sounds a lot like the argument I was trying to make to Norman.
Oh yeah, I see.
And what you say, that is what I think I believe, even with regard to certain other things that don't necessarily have to do with logic or accepting the truth of something or another, but whole programs or attitudes towards mathematics, because that exact thing you say, well, what does it lead to? I have a real problem with Grothendieck's approach to mathematics in general, and asking why, or searching for the right formalism. This is the thing I think doesn't lead to leads to definitions and objects that I didn't care about. I just want to solve problems. That is, and my view of the history of math is that's how good math has been done. This is a slightly different question than the kind of question you're talking about, but I use same framework to talk about it.
Right. Why? I mean, I think it's often the case, though, that it's worth thinking about these philosophical positions, because it might lead you to consider different mathematical questions than you would have if you hadn't been thinking about that. And then you can consider whether that's something that's worth pursuing more or not. And I feel, for example, I mean, I've been a defender of this multiverse view of set theory, and it's led me to really some extremely interesting mathematics about the modal logic of forcing, or the different questions about the way that different set theoretic universes can be related to one another, and also growing out of that to an understanding of the philosophy of potentialism, even in arithmetic. So if we view different models of arithmetic in a potentialist manner. And I view all of that mathematics as extremely interesting. And so I'm really glad that those philosophical positions led me to those views. So I wouldn't want to, I would argue against the idea that one shouldn't consider any philosophical position when you're doing mathematics, because oftentimes they can be quite fruitful and rich.
Well, I do think, and that's, you're somehow forced to, there's some questions a mathematician just has to approach in his work that I don't think are strictly answerable with regard to mathematics or a theory. I mean, need to form a conception in your head, what's important, what isn't, yeah, where are you going? What are you trying to understand? Is someone's work more valuable than someone else's? What's the key step? So you have to answer these questions, and yet we don't really have, it's not like we have mathematical tools to answer them. I don't know if these are the same kinds of questions you're asking about, but how about you? But it would really, the way I would like, if this set theory and logic touched something I recognized as being really concrete, the kind of thing I had to answer, and it has to be answered one way or another. I wonder if we'll ever see that. I mean, this question about these sets and whether they're measurable or not, and what is their Lebesgue measure, it's like it's almost there, and yet somehow those things don't seem to come up. I study functions, I try to solve partial differential equations, I take all kinds of limits, and it's never come up. And I'm really looking for, where are we going to hit that wall, like where it's just, we have to make a decision. I've heard things about Ramsey theory, which seems very concrete to me, and I don't know where that hits a set theoretic problem, and certainly I think in computer science and maybe some computable functions, the things I know nothing about, maybe they touch that. The only place, maybe I think, because I've heard you talk about it, I have a specific question for you, because one place that actually it has some logic issue came up. I don't know how important it is. I was doing a project in real algebraic geometry. Someone asked me a question. I was trying to solve this problem. OpenAI, a company, posed this problem on their blog. Can you tell? They want a program. They've actually wanted a machine learning trained algorithm to try to solve these IMO inequalities. You know what I mean? And it's really asking, is a real polynomial non-negative? which was
Right.
one of these things that, Hilbert studied. And there's this very interesting thing. Well, if a real polynomial is non-negative, you should have, it would be nice to have a certificate of it by writing it as a sum of squares. And you can't write it as a sum of squares of polynomials in general, but it turns out
Right.
they can be written as a sum of squares of rational functions. And that was proven, I think, fairly quickly at answering this Hilbert's problem. But the specific, how to actually tell and knowing what that denominator function is
Right.
something that I would really, want to know. And I'm not sure exactly what is the stat. I don't think you can tell what that denominator is for any given non-negative real polynomial.
Right.
And I was charged with trying to write a program. I did to actually determine that, and it seems like to me, it's I guess it's like a semi-definite programming problem,
Right.
but maybe there are some issues about the boundary of the cone of semi-definite matrices or something. And I don't think that the theory has actually answered in general, how do you find that denominator function to get that certificate? On the other hand, then I read, there's this like Tarski-Seidenberg theorem.
I was going to just mention that. Yeah.
And I don't know. I had no idea what these people were talking about. Would never have thought that logic enters into this problem at all.
Well, so there's this question of high school math identities. So you can set up a very simple language for high school real analysis. So you have, you can add and multiply, and you can do e to the x, and I think maybe trig functions and so on. Nothing esoteric, just and then you can form algebraic expressions from these terms, using those functions. And then you can ask, is this identity true? Is this term always equal to that one? Are they the same function? And it turns out that first of all, this is not computable in general. You can't computably decide that. And secondly, it's independent of set theory. You can find instances where the question of whether or not they're the same function is not provable or refutable. And it's sort of hard to imagine because it's really just high school math, nothing fancy. You're just asking, is this function equal to that one? And it seems like, well, couldn't you just test it? But of course, I mean, we're asking, is it true for every input value, right? Do we always get the same thing? And it's related to the MRDP theorem, the on Diophantine equations, right? So given a polynomial in several variables over the integers, does it have solution in the integers?
Can you say now, like looking back on that theorem, is it obvious that is the kind of thing like, that's undecidable because it encodes too much or something like that? I want to know, how do you know whether something fits into that framework, or it's just a theorem that we haven't proved yet, but we will prove?
I mean, the main thing is that the complexity of independent statements is very, very low. The threshold is very low. Any statement of the form, there is a natural number x such that, and then something computable about x. There can be statements like that are independent. Because inconsistency statements are like that. So whenever you have a statement that involves searching an infinite set, then the possibility that there is independence and computable undecidability has to be present. And so obviously these other statements are even way beyond that simple kind of quantifier, because we're talking about all real numbers and so on. So it's sort of a step up even. And so in principle, that level of complexity, could be independent.
I see. I guess I'm trying to justify why I roll my eyes every time that, every time there's like a big conjecture and it's hard to, and people are working at a long time and someone comes in, it could be independent or whatever. It could, I never think that it is in the kinds of things that I care about.
It's hard to prove independence results. I mean, it's a very, very subtle and delicate thing to prove any independence results. And so, well, let me give you one. I don't know how much time we have, but if you're interested, I can tell you a fascinating theorem that's not provable in PA. And it's another instance where this sort of,
Peano arithmetic, which is,
right, exactly.
I guess I don't know the exact relation to ZFC or
it's
whatever.
about arithmetic, about the natural numbers, and
Okay.
it's basically saying it's the positive part of a discretely ordered ring, and it has the induction principle. So that's basically what the Peano axioms say.
Okay.
Namely, we can add and multiply, and furthermore, we can do induction for properties that we can express in the language of arithmetic. So, right, okay. Give me your favorite number less than 100.
64.
Oh, that's a power of 2 already. So,
okay.
That's a great
67.
number. Okay, let's do 67. Okay, so 67 is 64 plus 3, and 64 is 2 to the what is it, 6th? Is that right? 2 to the 6th plus 3.
Yes.
Okay, so, but 6 is 2 to the 2 plus 2. All right, so
true.
Okay, so I'm going to write 67 as 2 to the 2 to the 2 plus 2 plus, and 3 was 2 plus 1. So I write it as a sum of powers of 2, but I also write the exponents in base 2 like that, and the exponents of the exponents and so on. That's called complete base 2. So what I've got here is, I don't know if you can see it here. Let me, let's see, let me just hold this. Okay, I don't know if you can see this. 67 is 2 to the 2 to the 2 plus 2 plus 2 plus 1 right here, right? Okay. And now let me tell you what Goodstein's process is. You replace all the 2's with 3's and subtract 1. Okay?
At the very end.
At the very end. So we have, so we had 2 to the 2 to the 2 plus 2 plus 2 plus 1. So now we have 3 to the 3 to the 3 plus 3 plus 3 plus 1, and then minus 1. So it's going to delete that plus 1. But basically, it's a huge number. I mean, it's 3 to the 3 to the 3, which is already enormous, and it's more than that. Okay, that's the next number. Now the next number after that is you replace all the 3's with 4's and subtract 1. Okay, so we're going to get 4 to the 4 to the 4 plus 4 plus 4, but minus 1. So that final 4, I don't know if you can see this or not. So this 1 here, we're going to have to take this 4 and turn it into a 3 in order to accommodate that minus 1.
Okay.
I don't know, maybe it's hard to see without. Okay, so we keep doing this. Replace all the 4's with 5, subtract 1. Replace all the 5's with 6's, subtract 1, and so on. Keep doing it.
I guess
Okay.
I'm wondering what is the meaning of the subtracting 1 and
The subtracting 1 has the consequence that every once in a while you have to break up the term. Like if you had 2 to the 2 minus 1, you have to break that up in order to rewrite it in complete base, whatever base you're at.
Okay.
It's going to cause you to have to break up the terms that came earlier, right? Like if I have 3 to the 3 and I replace the 3's with 4's, I get 4 to the 4, but minus 1. But in order to write that in complete base 4, I can't have this minus 1 there. So it's going to turn into 4 to the 3 times 3 plus 4 to the 3 times 2 plus 4 to the 3 times, plus 4 times 3 plus 3, right? I don't know.
Okay. I could. All right. Now I think I understand.
So the minus 1 is this really tiny thing that every once in a while causes you to have to break up the earlier terms. So the theorem is that you hit 0. It's an amazing theorem because it seems like these numbers are just getting gigantic. I mean, they are getting gigantic because we have 4 to the 4 to the 4, which is like bigger than the number of atoms in the universe or something already, and you just started with 67. So we're getting these huge numbers right away. And all we're doing is this minus 1 thing. It seems like it shouldn't have any effect. It should be completely swamped by the other part of the construction, which is replacing n with n plus 1, which is having huge effect, right? But nevertheless, the theorem is you hit zero eventually, because eventually this breaking up happens. It takes a long, long time. It's an extremely fast-growing function. But eventually it catches up. The -1 catches up. And then everything is broken up. And from that point on, you're just subtracting one forever, and there's no replacing going on because you're below the base.
Is this the same as, I guess I once heard someone explain cutting off the heads of the Hydra?
Yes, exactly. Yeah, that's an argument due to Laurie Kirby and Jeff Paris, and it's an alternative proof. It's a different way of describing the proof of Goodstein's theorem. So that one way of proving Goodstein's theorem is you take that number. Okay, your number was 2 to the 2 to the 2 plus 2 plus 2 plus 1. And we can associate that number with an ordinal, omega to the omega to the omega plus omega. Replace all the 2's with omega. So whenever you have complete base n of a number, you can imagine replacing all the n's with omegas, and that gives you an ordinal. And then you can prove that the Goodstein process from one number to the next, the ordinal always goes strictly down. Because now the n's are gone, because you replace them all with omega. You're just looking at the sort of the form of the number in the complete base n, but you're not paying attention to what n is. And you can prove that the ordinal goes strictly down at each step, but there's no infinite descending sequence of ordinals because they're well ordered. So you have to hit zero. So that's the proof. Basically, that's how you prove it.
Mm-hmm.
So this is an instance of what I was talking about earlier, where infinite objects have a consequence, these infinite ordinals. Tell us about this finite number process, the Goodstein process, which was totally finite.
Okay. That is that's a good kind of example, the kind of thing that I did not have at hand. I feel like that's the kind of thing that should convince some of these finite.
But the ultrafinitists won't like it because the numbers, like in a few steps, they're already bigger than the numbers that the ultrafinitists want to talk about anyway.
I see. Okay, still have a problem. It's
it works against the finitists maybe, but okay. But the other thing, because the Goodstein theorem has this second kicker. The theorem itself is shocking. Okay, that you hit zero. It's shocking. You can, when you understand the proof, you can see it's because the complexity of the form is going down, and that can't happen infinitely. So you have to hit zero. Okay, that's basically a way of understanding the proof. But the second thing is that you can't prove it in piano arithmetic. It's independent. So in other words, that's a way of seeing that the theorem requires this infinite stuff. It's not provable in arithmetic, in piano arithmetic. I mean, it doesn't require infinity because we could just add it as an axiom, and that's a theory that proves it, and it doesn't have any infinities. But one can understand the independence proof as suggesting that something fundamentally more than what we think of as ordinarily part of arithmetic is required in order to prove the Goodstein theorem, because it's not standard piano axioms.
Okay. Yeah.
I find this case really profound, actually. I mean, first of all, it's profound because it's an instance where the existence of infinite objects has this consequence down low, which is also true for these large cardinals and the sets of reals that I was describing before. But also it's profound because it's independent of PA, which ordinarily we think of as essentially complete for ordinary mathematical statements that we might want to consider.
Yeah, I very much want to admit the kind of question that this sequence asks, and I feel like it should have an answer. And you're right, it'd be too restrictive just to say about this piano arithmetic, thinking that was all because if you couldn't answer this question. I'm willing to admit the thing that answers the question.
It's provable in ZFC because ZFC has those ordinals, and you can do the proof in ZFC. So it's a statement about arithmetic that's provable in ZFC, but it's not provable in the usual axioms of arithmetic, piano arithmetic.
Okay, I like this example. I am glad that you explained this. Are you able to say, is there like one major problem in set theory today, or that people are working on, or there are lots of directions and problems?
Huge. I mean, so I made a post on Math Overflow because someone asked basically a question just like that a number of years ago, Math Overflow. And I think I listed like 15 or 20 different research programs that are happening in set theory. So of course, there's the large cardinal program and studying large cardinals and how they relate and the consequences of them and so on. And then there's the whole forcing program of looking for independence proofs and so on. There's also a subject that we mentioned earlier briefly called the cardinal characteristics of the continuum. So this is studying like the smallest size of a non-Lebesgue measurable set, or the additivity of Lebesgue measure, or what's called the bounding number, which is the smallest family of functions from the naturals to the naturals that have no function that almost everywhere dominates them. I mean, that dominates them except on finitely many sets. Or the dominating number, which is the smallest size of a family that dominates every function. And those are not the same. And there's dozens of these kind of cardinal characteristics, and set theorists are working to prove the provable instances. For example, B is less than or equal to D. The bounding number is less than or equal to the dominating number, but it's consistent that they're different. And there's dozens of questions in that subject.
We'll have to find a link.
Topics.
We'll find a link to that discussion, and
Sure,
I'll put it in the description. I'm so glad that we had this discussion. These things that you're saying, I'm at least, I have a lot of skepticism about set theory myself. It's useful, but at least I agree. You have some good distinctions. It sounds like you can say some things, and maybe someday it will touch something about functions that I really can't avoid. But it sounds like you have some good subject here. You have, so I know actually your Wikipedia page said you're the highest rated on this Math Overflow.
Yeah, that's right. Yes.
And maybe that's why these people I knew all separately, independently told me I better speak to you. Also, your Wikipedia page says that you are a public intellectual who talks on popular science media, and I don't know if this counts. I'd love to be counted.
It totally counts.
Among popular science. Someday it'll be popular. And you have you have books for people to learn about this stuff that will help, right?
2 books right here. I just brought them. So these are my 2 recent books. So this book, Proof in the Art of Mathematics, is a sort of undergraduate level mathematics book about how to learn how to write proofs. So there's many different topics, and I used it to teach my proofwriting class in New York. And then this book is Lectures on the Philosophy of Mathematics, which is the book that I use for my philosophy lectures here in Oxford on the philosophy of mathematics. So both of those are available. So please check them out.
Oh, do you know that I said something controversial in a video of mine where I was guiding people on the math major. I strongly recommended that people not bother with a course on just proof, how to prove things. It bothers me that there are such courses because, a lot of people disagree. I know students do need some initiation, I think, into some part of mathematics. On the other hand, I need content. I think maybe in the course of doing something that it's a concrete problem. Right. Unfortunately, these courses too often are just about formalism. This is what an equivalence really.
And that's why I wrote this book, because this book has genuine content. If you look at it, actually, my objection to so many of the other proofwriting books is that they're all about. For example, the other books are often organized by proof method, proofs by contradiction, proof of implication, and so on. But to me, this organization of mathematics is incoherent, because a given theorem might have 5 different proofs, and it would be wrong to suggest that it only has one kind of proof, and so on. So I have chapters here on, I do a little bit of number theory, prove the fundamental theorem, and I do some discrete mathematics and tiling problems, and I do graph theory, Game theory, I proved the fundamental theorem of finite games. There's a Pick's theorem, a chapter on Pick's theorem, and I have also, what else do I have here? Well, there's a chapter on, for example, if you have the integer lattice, okay, so the points of the integer lattice, can you make a hexagon, a regular hexagon? Like on your computer screen, that the pixels are, I think, an integer lattice. Can you draw a regular hexagon on your computer screen? I mean, a perfect one. And the answer is no.
Right.
You can't make a hexagon. You can't make an equilateral triangle. You can't make a pentagon, a regular pentagon. The only thing you can make are squares in the integer lattice, and so on. And so the question is, well, in which kind of lattices, what shapes can you make, and so on. If you have a hexagonal lattice, you can make an equilateral triangle and hexagon, of course. But that's it. You can't make squares there or pentagons or anything else. Okay, so, and then there's a chapter on real analysis and so on. So I completely agree with you. I think there needs to be content. And furthermore, my philosophy about proofwriting class is that the mathematics has to be compelling and beautiful. And so that's why I wrote that book, so that I could teach proofwriting in the context of completely beautiful theorems with elementary proofs. So I think maybe we're on the same page.
Okay, how quickly can you approximate a certain number with a certain kind of lattice? That's the kind of problem I like. But
oh, I see. Interesting. Yeah, I don't know.
Okay, good. I hope this answered some things for me. I hope this answered some things for my detractors who showed up in the comments of that other video. We learned a good amount. So yeah, thanks so much.
Okay, great. Yeah, it's a pleasure to be here, and really happy to talk to you. So hope everything works.
Great.